That would be original. Actually, that's what we should start doing. Yeah, for each place, always have like some kind of special local shirt, and no one can complain.
Right.
All right. Oh. All right. So it is my great pleasure to introduce Magdalena Balazinska.
Thanks.
Balazinska, right?
Oh, that's good.
Okay. Who is the Jean-Luc Barre Associate Professor at University of Washington, the director of the IGERT PhD program in Big Data and Data Science, and has received more awards than if I just list them all off, won't give her any time to talk, but awards from MSR, Google, HP Labs, the inaugural VLDB Women in DB Award just last year, NSF Career, 10-year most influential paper for code clone detection and refactoring, the PC chair of CIDR this year, numerous things. And on a personal, I mean, Magda is working on a ton of kind of practical applications of databases, and I think this is something that is super important. From RFID streams in the past and looking at different implications of what, there's about 3 or 4 different projects that started from that. Implications of what do you need to practically process data on streams of RFID tag data, and more recently on things that the intersection of economics and data management. 2 different projects there.
That's right, so a few projects.
And yeah, so today she's going to talk about a really cool system called Miriah, and let's give her a hand.
Thank you, Oliver, and thank you everyone for coming. So it's really my pleasure to be here today and have a chance to talk about some of the work that we have been doing in the database group at the University of Washington. So as we all know, it's a really great time to be a database person because we live in the world of data. So everyone has some kind of big data problem. They have this problem, whether in industry or in sciences. Often people have so much data, they refer to it as a data lake. When the data is continuously arriving, then it's a data stream, and when they cannot get their work done, then it becomes a data swamp. But however people call it, there's definitely, we are in a world driven by data, and therefore it makes it very exciting to be among the people who build new systems to help users manage and analyze this data. So being on the university campus, what we really work on is really to collaborate with scientists in different domains and understand their data science challenges, so their data management challenges. And they have very many interesting challenges. So if we start as an example from astronomy, they do a lot of work working on telescope images where they have actually the pixel data, and they need to do all kinds of management and analysis, including detecting sources in it, doing iterative data cleaning, object kind of extraction, classification. Still in astronomy, as another example, very large data sets come from simulations of the universe. So here we have large tables with particles in 3D space. And then what we need to do is, kind of the simulation runs, it outputs data every few time steps. And what we want to do as an analysis in particular is kind of understand the evolution of galaxies, which really means we need to do clustering in the space and then graph analysis to understand kind of how these clusters evolve over time, and this is how galaxies evolve. As another example, in neuroscience, people work with MRI data, where once again they have to do all kinds of pixel level data, cleaning, smoothing, and also building machine learning models. And many of these challenges kind of go beyond the applications that we find on campus. But the bottom line from all this exciting science from the database perspective is that users have big data sets, they want to analyze this data, and they need to manage this data. How can we help them with it? So as database people, we can help along 2 dimensions. We can help with the efficiency. Can we build systems, data management systems, that will help them get their work done faster? And the second thing is ease of use. Can we make it also easier for people to actually do their data analysis? So in our group, we have actually looked exactly at this problem, and we built our own stack for big data management and analytics called Miriah. This is an open source system that you can find on our project website. The goal really is to advance the state of the art in database systems, in how to build systems for analyzing and managing kind of more modern data sets in the context of modern application requirements, with this focus on both productivity and efficiency. And one of our goals in Miriah was to say, look, we really want to build our own platform for research. So Miriah at its core is going to combine design decisions that are just kind of the commonly known design decisions for how to build big data systems, and also kind of innovations on top of that. As deliverables, we build the system, we run it as a cloud service, and it's also available open source. So Miriah is a collaboration between the database group and our eScience Institute. So it was developed jointly and is operated jointly. And my co-PIs are Professors Dan Suchu and Bill Howe. So before I go into more depth, since many of you have not seen Miriah, let me give you a short demo. So the example here that I like to start with is actually a few weeks ago, I was at a conference, and as I was sitting listening to one of the talks, the speaker was talking about the Twitter graph and different properties of the Twitter graph, and I kind of thought back about Twitter and said, right, so this is a graph, and I remember someone talking about the connected components, and I was kind of curious about the distribution of these connected components, and I have access to this data set, and I want to recall this result, but here I am, stuck in a talk. I can't walk out, but that would be rude, plus I want to hear the end of the talk. But I have only my laptop. This is a new laptop, so I had basically nothing installed on it, so what can I do? Well, one thing I can do is I can definitely pull up my, let me just exit the presentation. So I can pull up the browser. I can definitely open my browser, so I can open my browser, go to our project website, and say that, oh, I would like to actually try the free tier of this Miriah service, so here it is. And this gives me kind of a web interface where I can directly go and start to poke at my data. So my data here is not loaded in the service, it's running on Amazon, but I have my data in S3, which is just this standard place, storage in the cloud where we can put data sets. So that I can tell Miriah, say, look, I actually have this data set in this S3 bucket, and this is what I would like to analyze. Because I'm going to do a lot of analysis, I would like to actually parse this data, read it, and then just store it internally in the cluster, because I'm going to run many queries. So if I do this, this is a real demo, so it will either work or not, we'll see. If it works, it's because our system is great. If it doesn't work, it's because the wireless doesn't work very well. At least it's running, so at least there's something. So let's see what happens. It should be pretty quick.
Our Wi-Fi is slow.
Could be that the Wi-Fi is slow, so let's give it another second here. Let's see if we can. Let me close this and let's try again. So we have this data set, so let's actually see if I can execute it. Let's see what happens.
It doesn't ask for authentication, so basically anybody can.
Correct. So this is a really good point. So this is kind of our trial version of the service. In the trial version of the service, we don't use any authentication. So if you're pointing your data at a bucket, it has to be a public bucket that you don't mind other people looking at your data. For some sciences, it might not work, like if you have some kind of confidential data. But for other scientists, this actually works perfectly fine, like for astronomy data. The
I'm
data
surprised you let anybody run up your AWS build.
Oh, no, this is actually fine because we have a cluster this is a cluster with 5 machines. So we constantly pay for a cluster of 5 machines. So it's not going to generate more cost. And it actually is working. So kind of it worked successfully. Maybe the wireless was just a bit slow. But what happens now is I can actually go and say, okay, I've loaded this data set. So if I go to see what data sets do I have in this cluster, so again, what we have here is on the Amazon cloud, we spun up like a small 5 instance version of our service, and I want to use it to analyze my data. My data started in S3, and all we did so far was say, my data is in S3, can you pull it in the cluster? And then when I look at the data sets in the cluster, if you look at this Twitter-K data set, which I can see this is my favorite example, it has just been updated. So if I click here, which I won't do because if the internet is a bit slow, I want to pull those results, I can see the data. So now my data is in the system, so I can start to do some analysis, and we provide many example queries for people to get started. So here's an example where I can run a query maybe to just get some of the columns, run some simple aggregations on the data to get some idea, maybe do some joins, in this case kind of self-joins to get some interesting properties. I can get a little bit fancy and write my own, my own user-defined functions, all the way to finally this graph, which is completely by coincidence exactly the query that I need, which is going to look at the connected components. So let's look at this example in some more details. The actual details of the computation are not quite as important as what we see here is that each of the statements in this analysis script is basically a declarative query. So think of it as SQL, and you can write SQL. In this case, we write Miriah, which is kind of our variant, but also declarative relational language. But the difference is that in addition to just declarative statements, I can also have some imperative constructs like variable assignments and importantly iterations, which allows us to write kind of much more powerful script. So here I can actually run the query. So let's see if that still works. I can actually execute the query to compute these different connected components. And this is what we'll see. If you have better access to the wireless, I invite you to also try this after the talk, and it should be running pretty rapidly. Let's see what happens here. It's running.
This is connected component query?
This is a connected component query, right? So I don't know what's wrong. Maybe the wireless is a bit too slow for the system. I just gotta pull it up here. So the other thing that I want to look at, so this is, so the query normally runs pretty rapidly, so I invite you to try it maybe with your better connection. But what is important is that here so far we have seen that I can just, all I have done is I installed nothing, I just open my browser and I can start to do this analysis. And that's the kind of ease of use that we are talking about, that we are targeting here. Of course, when people do data science and true data analysis, they will come back and say, well, this is nice if I just want to explore my data. But when I do my real job, I actually don't use this kind of web browser interface. Typically, I'm going to write Python scripts. In particular, I'm going to use, that works. So then I'm going to blame it on wireless, since it actually does our work. It was just a bit slow. But what happens is then people say, look, when I do my real job, I'm not going to write these kinds of queries. What I want is really look at it from Python scripts, and in particular use this novel tool that's very popular today called the Jupyter Notebook. Also, it used to be called the IPython Notebook. So we added this where I can just go and have one button and actually pull up a Jupyter Notebook. So this actually pulls up the Jupyter Notebook. And that's going to allow me to write Python scripts directly in the browser using this tool. For those of you who have not used Jupyter Notebook, just think of it as a convenient way to write Python directly in the browser.
So, Magda,
Yes.
your like the typical application area folks use Python regularly, or?
Right. So basically, when we work with scientists on campus, that is their kind of main tool.
Right.
Their main tool today is to use Jupyter Notebooks. So they're very excited for us to be able to kind of provide that functionality, all without people having to install anything. And that's really what's important. Okay, but you have seen enough. So there's a little bit of kind of slowdown with the network, but I think this is kind of, people should get an idea. So I invite you to kind of try this tool on your own.
What would be the output from that query?
Oh, this output of that query is just kind of the ID of a component and the number of vertices in that component. So that's it. And actually, if you run the query here, you'll see that Twitter-K is actually a subset of the Twitter data set, so the result is going to be just a few components because it's a small subset for demo purposes. Okay, so as you have seen, kind of this is just going back to the talk. So we provide Miriah as a cloud service that the goal is for people to, I basically tell my students that the goal is for me to be able to give demos at the airport. That's kind of how easy it should be. Like in difficult circumstances, where I can't actually demonstrate, can't download anything. So we support analysis directly in the browser that can pull data directly from S3 so that it's very easy to get started with the analysis and actually go up to writing even reasonably complicated scripts. Something that I have not demonstrated, but I invite you to poke around the tool, is we also provide query profiling features where users can run queries, profile them, and really understand what's going on, how many machines are executing, what's happening in their queries. And this is the example of this Jupyter Notebook connection, where if you click on the Jupyter Notebook button, then you get to see this perspective from Python where you can issue queries. One feature that we have added recently, specifically because it was really important for users, is that you can write Python user-defined functions and then call them directly from queries. And this is important because in many cases, especially in the case of image analysis, our users already have pipelines where they do complicated analysis, and their analysis is not easy to rewrite. Like if they do some kind of denoising, it's not just an average, it's going to be some kind of kernel and some complicated functionality that no one wants to rewrite. So we want to just wrap it and be able to call it, and this is something that we do provide. Once users outgrow our sample demo cluster that we offer, they can install Miriah and create clusters on their own. And we have used Miriah so far for different applications, from natural language processing to neuroscience, a lot of work in astronomy, and also a lot of work in oceanography, some of the examples, and then some work also in bibliometrics. These are example applications and groups that we have worked with. So now let me turn and let me actually pause here and see are there any other questions regarding just using Miriah or that interface, or are people ready to go into the internals? All right, so basically we have this tool, which is a database system with the goal of having an easy time interacting with it. So let's see what we are actually doing internally. So internally, Miriah is actually what is called a polystore system, which means when users issue queries, so you're going to write queries directly in the browser, maybe using Python, or we also have built over time different specialized services. We receive this query and we have two components in our system. One will do all the query optimization, and the component called doing query optimization is called RACO, for Relational Algebra Compiler. It has relational algebra with iterations at its core, and it's going to then generate query plans either for the Miriah on our own backend, which is called Miriah X for query execution engine, which is this parallel, iterative, elastic, shared nothing query engine. But it can also generate query plans for other backends, and we can even support now query plans that cross between these different backends. The demo online is set up only to use Miriah X, but we have other deployments that do this, cross-system query execution, and this is why it's called a polystore, because it doesn't have its own store, but it can also communicate with other stores. And this is important because users today have actually access, and their data is located in different systems, and in many cases different systems have different functionality that you might find convenient for certain tasks, so we want to make it easy to leverage these other existing tools in the ecosystem. If we focus on the Miriah X engine, specifically, it's a pretty standard shared nothing engine where we have one coordinator that receives the query plans and many workers that work together to execute the plans. And these workers can read data, as we have seen, from S3 or from local HDFS. Internally, they also use relational databases for local storage, which we use like a cache, where when you pull the data and you say maybe hash partition it, reorganize it in a cluster, and then store it locally, we will use this more efficient storage as opposed to rewriting back to HDFS, and we can use indexing here and so on. Once we run queries, we're going to use a pretty standard parallel database approach, where our query plans take the form of these graphs of operators. Each operator is a relational algebra operator or a user-defined operator, so selections, joins, etc. And we're going to actually read the data, and the data will be pipelined. We're not going to materialize data to disk if we don't have to, including having exchange operators that we call shuffles that are going to reorganize the data across the cluster, perhaps if we need to bring different data sets together for joining. So just to think about that, the data starts from disk and is going to stream through all these operators to give us the answer. So that's really the high-level architecture. Now, let's really focus on some of the interesting, more innovative components of our system. So in this project, we are innovating at least along 3 dimensions. First is, of course, we are database systems people, so we want to build new algorithms to efficiently process different kinds of database queries. In particular, we have looked at complex multi-way join queries. We are looking at data summarization, image processing, as I have shown in the example, and the one I'll talk about this are iterative queries. We also have another line of work on this federated data analysis, where how do we kind of run queries across multiple backends, generate data for different backends, and I'll talk about one specific project, which is how can we support efficient cross-backend queries by moving data rapidly between different backends. And finally, as you have seen, we run Miriah as a cloud service, so there are a lot of interesting challenges in how to offer database systems as cloud services in a way that's easy for users and also cost-effective for the provider. And once again, kind of at the high level, this is kind of a broad collaboration with Professor Bill Howe and Professor Dan Suchu, looking at different aspects, in particular kind of other federation aspects, theoretical aspects, and then myself kind of also in this space. And there are also more projects that I'm not mentioning here on this slide. So let me actually spend the rest of the talk talking about kind of mostly iterative processing, and then this data pipes, and then very briefly about the cloud operations. So let's start with saying, okay, I have this great system. It's called Miriah. I can use it through the browser, through my Jupyter notebook, and I actually don't want to do simple select, project, join queries, but I have complex analysis that I want to do. In particular, in many modern data analysis systems, I need to do iterative processing. So one example is the connected components example that we have seen. A very simple way to implement this would be to start with a graph and give each vertex a unique identifier, and then iteratively have each vertex broadcast its identifier to its neighbors, and then each vertex looks at everything it has seen from its neighbors, and it picks the lowest identifier that it has seen and reassigns it to itself, and then rebroadcasts it to its neighbors. And if we keep doing this, eventually everyone is going to converge that if there's a connected component, everyone will have the lowest ID that was originally assigned to any vertex in that component, and then the system will converge. There will be no further changes. Similarly, in astronomy, we also have an example of an iterative processing. We start with a table of particles. These particles are assigned to clusters that correspond to galaxies. What we need to do is kind of join time steps with previous time steps to find overlap between these clusters, and by doing so connect edges, and then do this recursively kind of until the beginning of time to find this merger tree for this galaxy that we start here at present time, kind of see how it has been created through the mergers of older galaxies. So this is again another example of an iterative query. So the bottom line is that we as users want to run these iterative queries in the system. When we started to look to work on this project, we looked at existing solutions, and there are many solutions in this space, but none of them was really satisfying all of our needs. So many systems, right, provide iterative processing, but they only provide synchronous processing, where we're going to do one iteration block, another iteration block. But we know that for many algorithms, connected components is one example, if we can process in parallel in an asynchronous fashion, we should be able to get faster runtimes. So we wanted to support both synchronous processing, where we do one iteration and block, and asynchronous processing, where we could just generate facts and aggregate those facts continuously until convergence. Many systems are looking at a single node, but we definitely have a shared nothing system. There are also a lot of very interesting works in systems, but they don't provide a declarative interface. It's really up to the user to combine operators in a way that is going to answer their queries. But we want this to be easy for users. We want them to just write what they need declaratively, and then for us to actually generate the query plans for them. Many systems are specialized for graphs. We don't have only graphs, as you have seen in some applications. We start with just a relational table, like a table of particles. Some are not data management systems, and there's also a lot of kind of very interesting theory. So what we decided to do is say, no, we actually want this kind of full stack solution where we're going to allow the users to start from a declarative layer. We're going to then compile this into a query plan, and we want the query plan to be easy to implement. We want kind of small extensions to existing data flow systems that will allow us to add this iterative feature. I don't want to rethink the system completely. And then we want to support efficient optimizations, like choosing between synchronous and asynchronous processing. So what we have done is basically the following. So users are going to express their computations. The computation is really expressed kind of in, so it's data log with aggregation and recursion. There are kind of constraints on what we can support. typically the main constraint is that we need to have kind of good monotonicity properties, that as we iterate, because we're going to iterate asynchronously, we want to make sure that the query generates new facts and aggregates the facts, but never kind of withdraws, kind of have negations that requires us to withdraw facts. So here's just one example. Of course, in our system, we're not going to ask users to write data log, they're going to write this declaratively. So this is the connected components example rewritten in this kind of more efficient way that will allow us to support both synchronous and asynchronous processing. The previous version was purely synchronous processing, so more general, but only synchronous. This one is more specialized, but will allow this optimization. So here we say that we want to compute these connected components. What we're going to do is start from assigning, we start from the edges, where we will kind of extract the vertices and to each vertex assign its own ID as the component ID. That's how we're going to start. And then at each iteration for each of these vertices, we're going to look at the minimum value across all the component IDs that it has received from its neighbors. And as we generate those, we're going to kind of generate new component IDs for each vertex. And then we're going to iterate and say, well, take these new facts that you have discovered, join them again with the edges to propagate this to your neighbors, so that now they will receive this information, and they're going to do this until convergence. So that's kind of at a high level the kind of queries that we will support. Here, basically in the body, we're going to have select, project, joins. In the head, we do support some aggregations. And as I mentioned, and the paper has more details, that there has to be monotonicity properties that we basically continuously just generate new facts and aggregate new facts, such that we can do this until convergence. From this, we're going to generate the query plan to actually execute this efficiently. The key idea for our query plans is that for each of these relations that we're going to compute in this iterative fashion, we're going to kind of keep updating until convergence. We have one operator that is specialized and that we call an IDB controller. What this does is basically accumulate the state, and every time we discover changes to the state, we're going to output only the deltas. So we're only going to output the changes to the state, and then the rest of the query is going to be select, project, joins, which will naturally give us similarly kind of incrementally generate new facts based on the ones that we are discovering, and we're going to feed them back. So what is nice here is we start from a declarative specification that we convert into a shared nothing plan that is very similar to regular shared nothing plans with this extension of these extra operators. We also have a separate operator to determine when we have converged, but it's less interesting, and so kind of we can see there's a second operator here that I'm not representing, but these are really the only two choices. What is interesting is with this technique, we can actually support plans that have multiple relations that we want to compute recursively, and they can depend on each other. And we're going to generate query plans that may then potentially have multiple of these IDB controllers. So the second step that we want is now we want to support both synchronous and asynchronous processing. In this case, we know that what we start from are applications that can be executed asynchronously, so we know that this is going to be correct, but we may still want to choose between these kinds of processing, as you will see in a few seconds, that this is going to affect performance. So the IGB controllers are going to regulate whether we're going to process synchronously or asynchronously. To process asynchronously, we will simply start with the initial data set, and then as we discover new facts, new tuples, we're going to propagate them. We will kind of generate more data, and all the IGB controllers will continuously generate new data without any synchronization until everyone has converged and no one generates new data anymore. At that point, we will stop. If instead we want to do things synchronously, as soon as this IGB controller is done reading its input data, it's going to generate an end of iteration, and then we're going to generate more data here, but the IGB controller will only accumulate data and aggregate it without generating new outputs until this end of iteration comes back. And at that point, we're going to say, okay, we are done with one iteration, so in one bulk, in one go, we're going to now generate all the outputs for the next iteration. And that will give us synchronous processing. So what is nice is we start from declarative, we go to this query plan, and we can execute it both synchronously and asynchronously. Yes?
This is just a clarification question. So you support both asynchronous processing and
Correct.
synchronous processing?
Correct.
is there a way to express that from the user side, or do you just determine that automatically, or what's the?
This is a good point. So at this point, there isn't a way, and we basically have a flag to process this synchronously or asynchronously. So like I think in this case, in the system, when you actually write the computation, it's going to process it asynchronously. And you have to set it, but I think this is a good point, and yes, we should have that so that the user can control this. At this point, it's not controlled, and we default to 1. And we've compared with both in our experiments, because it's not always the case that asynchronous is faster. It really depends on applications.
Okay. So is it just about performance? So there's no correctness concern about?
So in this case, we restrict what you can express only to applications that we know we can process asynchronously. If you want to process something that would be incorrect to process asynchronously, then you will not be able to use the syntax. You will have to use the general syntax that I showed at the beginning that allows you to do whatever you want, but it's going to do one iteration stop, next iteration stop. So basically in the Miriah system have kind of partitioned. Either you do whatever you want and it's synchronous, or you can only do a subset of computations, and then we know that you can run them asynchronously. Yes?
Comment and possibly a question. Using the previous syntax, can you exploit something like the delta computations that you're using here to optimize
Yes, so this is a good point. So iterative processing is typically done in an incremental fashion. We don't want to recompute everything, only the changes, even when we do it in a synchronous fashion. In the previous syntax, it's up to the user to express the deltas and say, compute this, and I subtract this. So it's manually. We don't automatically make it incremental. Although this is something that we could add. In this case, it's going to be incremental.
Okay. And how are you, is it up to the user to enforce convergence on the delta tables, or does the user have to write code? What happens when the user gives you a query that doesn't converge?
That's a good point. So we are basically, in this case, it's up to the user to give us the right kind of queries. We do not perform those checks automatically. We do provide very restrictive syntax to make sure kind of steer the user towards programs that are going to be very easy to verify even manually that they should be converging or not. Because the main thing is you have to do things that are monotonic. So if I generate kind of new aggregates, I want these aggregates to move in a certain direction. So minimum is good because it always is going to always go kind of over the lattice towards one bottom element. Same for maximum. We can also do the same for counts, which actually we had to do for certain applications because we had to increase counts. The counts will continuously grow because as we discover new, for example, looking at different clusters, if you find more particles that are shared between the clusters, the count of the shared particles grows, and then we can accumulate that count, and we can say, okay, once the count reaches a certain point, now you can generate that extra galaxy as another ancestor, and that would also work. So the bottom line is here, we do not automatically enforce, so the user could write something potentially incorrect. We could further reduce it, but here we basically tell the user, look, what you can really do is in your head you can have aggregates, and then the rest has to be monotonic with respect to what you're doing here.
Okay, so the head has to be an aggregate computation.
The aggregates are only in the head. And then if you don't put something,
I see.
it's going to be duplicate elimination if there's no other aggregate.
Right.
Other questions? So let's look at the actual results. So here what we have is this flow. We start from this declarative query, generate these shared nothing plans, and you have this option to actually do them synchronously and asynchronously. And actually for the asynchronous, we also have two ways to prioritize the data. So let me go back here. If you look at this join is going to get data from two inputs. The input that come from disk, and then this recursively computed input. So the join has different choices. It can either try to first process all of this data before getting started on this. Or it can say, no, as soon as I get any data here, I'm going to favor it over the data that I have. So we can prioritize different data sets, different inputs, and as we will see, this actually also affect performance. So let's look at a few results. So the first result is this example from this galaxy evolution. So we have kind of an example from this astronomy simulation. It has 27 time steps, and we want to go back and find the evolution of some galaxies. We're going to use a different number of workers, but what is interesting here is we're going to do this computation either synchronously in blue or asynchronously. And the result here is kind of exactly what we would expect to happen always, which is that the performance is similar, but if I can do this asynchronously, maybe I have some performance gain because I don't have the synchronization barrier. So that's kind of the result we expected to find for all the applications. But then when we run it on other applications, like the one from bibliometrics, where the goal is to find for papers that cite other papers, kind of go back the citation graph to the least common ancestor, the closest ancestor in the citation graph, we actually found the opposite trend. So this is now asynchronous and this is synchronous, much faster. So we asked the question, why is it that for this application, synchronous processing is much faster? And what happens is in this application, we want to find the closest ancestor and stop. So if I do this in a synchronous fashion, I'm going to do one time step at a time, go back one level of citations, 2 levels of citations. As soon as I find the common ancestor, I stop for that pair of papers. If I do this asynchronously, we're going to start to find all kinds of ancestors far into the past that we don't need. So with the asynchronous processing, we end up generating significantly more intermediate results that end up being pruned. Versus synchronous allows us to do this pruning at each time step and ends up being much faster even though we have the synchronization barrier. And finally, the last result here shows this our connected component example, where it is known that asynchronous can be much faster. But here's what's interesting. So this is the line for synchronous processing, and this is the line for asynchronous processing when we prioritize these newly discovered facts. And this is asynchronous processing when we prioritize the data that we're kind of slowly reading from disk. So what is happening here is, again, a kind of problem with how many intermediate results we are generating. As we have the connected components, if we take the lowest connected component find so far and try to propagate them as fast as possible, as far away in the network, then we end up having very good performance, as opposed to trying to make sure we propagate all the connected component values by one step and then one step. We want to kind of prioritize the lowest values so far over all the other values, and that gives us this improved performance. So what is interesting in this paper is that we basically kind of close the loop and say from declarative queries all the way to these plans that allow this optimization, that allows us to kind of give us good performance numbers for different kinds of applications. If we compare this to other systems, you might say, well, maybe Miriah is, is just really slow or really fast. So here's one example graph of us against Spark on this connected component example, and we use the GraphX version, which is the kind of graph optimized version of Spark. And what is interesting is that if you look at the synchronous way of doing processing, that we are indeed similar. Maybe a little bit faster in some aspects, but depending on the cluster configuration, roughly equivalent. But then what we can do is we are not only restricted to the synchronous, we also support asynchronous, which can give us kind of significant performance gains. And that was kind of the bottom line. And for more information, I invite you to read our VLDB paper. So in summary, for this processing, we kind of, it's important because it occurs in many applications that users need to do iterative processing. We strive to go from the declarative layer all the way to this efficient, optimized share-nothing implementation.
So
Yes.
Does this also support nested loops, or?
So we can definitely have kind of different relations that depend recursively on each other.
Okay.
So that's what we're going to support. But in the body of the query, we support simple select, project, join query, no complex subqueries there.
Right.
So only select, project, joins with aggregates, but they can be interleaved. We found so far that this was good to express many computations that we care about, but definitely that's the limit of what we can do. Yes.
Is there a transformation layer that you can join different data sources together? Different types of data sources like graphs and DB, for example?
So this is a good point. So the question is if you can combine different data models. So our engine is a relational engine. So we're going to treat everything as relations. For some, like a graph, for example, then a graph is basically a relation because it's just a set of edges. So we would be able to combine graphs with other data sets because we would view the graphs as just edges and vertices. We also provide other data types, like, for example, images. For images, we have two choices. We can either view them as individual pixels, or we also support blob data types, which allows us to chunk images into fragments and then runs user-defined computations in Python directly on these fragments without any data conversion. And this is actually a perfect segue because that's actually an interesting question, right? So what if I have data kind of that maybe uses different data models, and then there's Miriah that's very good for relational data, but I might actually want to use a graph engine that's really specialized for graphs for some part of my computation. Which means what I want is be able to do this kind of polyster analytics, where I'm going to do analysis across multiple backend engines. So let me give you a motivating example. So going back to this astronomy simulation example, we have our n-body data, so data coming from this astronomy simulation. One typical workflow is to compute distances between nearby particles and then cluster them differently, and then kind of look at the clustering. And the clustering is actually such an important component that astronomers apparently even have whole conferences on the best way to cluster the data set and all the different implications. In this example, we can immediately run it and do some clustering with Miriah. For example, connected components would be one example. But what happened is actually Spark, which is this new engine, has also different kinds of clustering algorithms, and they have some specialized clustering algorithms that maybe we want to try. So as an astronomer, what happens is now I have my data in Miriah, and I've been doing my analysis, and I discovered that Spark has this interesting clustering algorithm. I don't really want to just move all of my data and just rewrite all of my computation in this new engine. What I would like to do is for this specific step say, well, continue to do my pre-processing here, but can you just run this clustering algorithm from this other engine? And of course, we can do this because what we can do is say, well, let me run this initial pre-processing step in Miriah, and then let me just write this data out to HDFS. And then once it's in HDFS, write the result of the query, then I can read it from Spark and I can run my clustering algorithm. Of course, this is where we go back to this kind of data format problem. Well, of course, I have to write it out in a way that Spark understands. And you can imagine kind of different possible formats, but when we looked at many engines that exist out there, they cannot agree on any kind of format except for CSV, right? Comma separated values. Which is going to be this text-based format. So what I have to do is really take my data, output it on disk in this text format, and then I will be able to re-import it. And that will work, except it's really not going to be efficient. So this is one example it's on a single machine on 100 gigabytes of data, where it takes me about an hour to run the pre-processing step. This is just one machine in this experiment. Maybe 45 minutes to do the clustering, and just moving the data is another hour. That's a huge difference, right? From like 2 hours to 3 hours, just because we had to move the data. So what we would like to do is say, can we instead have a faster way to connect these engines, such that we can cut down on this runtime? Maybe not completely, but kind of cut it as much as possible, such that my computation is really the computation that I care about, and I don't even notice that I'm moving between systems. And of course, one way is just for me to, open my Eclipse and kind of write the code for this, specialized operators, or more accurately, for me to email my graduate students to implement this kind of, specialized connection between systems, which would work if I always want to work between Miriah and, for example, Spark. But there are other systems out there, right? What if I want to use Giraffe or SciDB or some other systems? I would have to write these specialized connectors for all pairs of systems. And we wanted to avoid this. We said, look, we want to do analysis across systems. The landscape of big data systems is large. Can we automatically generate efficient connections between any pair of systems? So that was the goal of our PipeGen project. And similarly to Miriah, whose source code is available online, the PipeGen source code is also available online on our project website. So the key observation with PipeGen is that, as I mentioned, all systems at least know how to export to CSV. Can we look at the source code they have to export to CSV and use that to understand their internal data formats and basically intercept the data and kind of add code that is going to, instead of exporting to CSV, basically send it as binary? So that was the key idea, and that's what we did in this project. So we have the PipeGen tool, and it's going to be used in 2 steps. There's first an offline phase, where we will take the bytecode. So this is targeting Java-based systems, like Miriah, Spark, Hadoop, and others. We're going to get the bytecode of that engine, and we're going to also use unit tests. What is interesting is all these tools are open source, but they all follow good software engineering practices, and they all have unit tests to test their CSV export and import. So we're going to take their unit test and their bytecode. We're going to run the unit tests but instrumenting the bytecode, such that we're going to run a unit test that says export this file to write to disk. And as we do this, we will instrument the code so that we'll be able to intercept and see this is where the source code lies that actually does this export. Once we do this, then we can start to modify it. In particular, saying if you export to a specific file name, instead of writing to disk, why don't you open just a socket and start to write this data to this other system? And of course, once we do this, we can start to do all kinds of optimizations as well. So after transforming the source code, we now have a database system that has been extended. We have added more code to it to do this more efficient data piping. So now at runtime, what the user will be able to do is have the two database systems. Each one can be a parallel system. And we're going to run one query to one system that says, okay, so scan my particles, do this preliminary distance computation, and export. But don't export a random file, export to a file that has a specific file name that basically says, names the other system. And the other system will receive a query that says, okay, import the data from, again, the special file name, and then continue the processing. If we do this, then the system will execute the query that will include the export operator, but that export operator has now been extended with our code that will notice that there's a special file name and will open connections to the target system. How do we find the other target system? We use a kind of separate directory system to kind of connect the workers together. So let me give you more details on the transformations that we are doing. So here we start with this, the GBMS bytecode. As I mentioned, we will run the unit tests, but we instrument them. If I instrument unit test, I can find the line of code that says open file, write to file. If I do this, I can say if special file name, don't open the file, open socket. Right? So that's what we're going to do, and that is going to allow us to already have these connectors that will send CSV data, but at least not going through disk. That's step one. If I do this, I can say, well, wait a minute. I now see the line of code that says create the CSV file, right, and send it. So can I go from the string that you're passing and walk my way up the source code using data flow analysis to find the original objects that you're trying to send? And why not just send these objects directly in binary format, avoiding delimiters, avoiding translation into text? And that's what we're going to do with this optimization path. So how fast does it work? So first of all, it actually works, which is really exciting. So we took 5 systems, and then we, instead of having one graduate student prepare a system, implement something manually, we used the Python tool to generate these efficient connectors, so 20 different connectors between all the pairs of systems. And then we try to move data between them. In this case, we are moving a synthetic relation that has, I think, many tuples. Each tuple has 4 integers, 3 float values. And what is interesting is we consistently find approximately a 3x speed up compared to doing this export to CSV and import back from CSV. And I was actually surprised to see that this was kind of so consistent. If we zoom in into one of those bars, we have the following. So here we have for different data sizes for this relation that we are transferring, using different techniques. So the top lines say export to disk and we import back from disk using either local system or HDFS. And the blue line shows what happens if instead of going to disk, we simply open the socket and send the data. So huge performance gain just from avoiding writing the data to disk and sending it across machines. But then there's also another maybe 30% further gain by having these additional optimizations that say don't even write text. Can you go back in the code, intercept the data that you want to send it, and directly send that binary data? And this comes very close to kind of a pipe that we tried to write in this kind of manually optimized fashion. Right, so kind of overall, kind of the summary for this component is that there are many reasons why people might want to use multiple systems in the context of their analysis. If you want to support that, there are of course many challenges, but one of them is if we cannot move the data between systems efficiently, there isn't much we can do. So in this project with the Python tool, we addressed that challenge and said, can we automatically generate efficient data pipes between combinations of systems such that we can integrate them more efficiently into this polystore?
How reliable is how reliably can you pull this information out of the test cases? Or pull the
So that's actually, it's an important question, is even how do we verify that the system is working? So the way we verify that the system is working is we're going to, we have kind of an extra component that can just receive CSV and go back CSV, kind of return the CSV. And what we're going to do is run the unit test in two ways. One, by basically just run the unit test normally, and then we can check that the unit test works. The other way is, instead of sending the unit test just straight to disk, send the output using this binary format to our extra verifier that will then write the CSV to disk, and then we can use the kind of standard unit test checks to make sure that it's the same file. So how well does this work? It kind of depends on the unit test so far. If the unit test has a good coverage, then we're going to also similarly verify that we provide good coverage. If the unit test is missing something, maybe no one ever tested transmitting Boolean values and there's a bug in transmitting Boolean values, then we won't be able to verify this. However, what is interesting is if the user has a specific query that has specific needs, well, they can use a sample of the data for their query to also verify that the export to disk and the modified one that we provide are going to generate the same data. So that's how, so kind of, we are limited in the unit tests that are provided, but we can grow this set of unit tests as every time someone has a new query, if there's something that wasn't covered before.
So the only human interaction here is identifying the CSV files and then hitting go. Is that
Right, so basically you have to tell us, this is the source code of my database system, those are my unit tests. Do it, and then once you do it, then you can say, okay, now I'm going to submit one query with this special export, one query with this import. It's a very cool system, I'm very proud of it. And we actually released it, so you can actually try it. Please try it, and then cite us. No matter what you say, because they actually don't check if it's a positive or negative citation. Okay, so in the last 5 minutes, let me just tell you something very, very brief, just to give you a taste that we also work beyond the core of the engine, actually looking at, in this case, the cloud operation aspects. So the idea with the cloud is, how should we actually, right, it's very easy for me to offer a service for free. Say, open your browser, go to our project website, click here, and then I'm paying for it. Right, of course, that's easy. But then what if I want users to actually start paying for the data? One challenge, the user has to figure out, well, how many machines should I use, 10, 20, 30? And there's so many different instance types. It's a very hard problem. So we believe that this is the wrong interface. What we want as an interface for Miriah is for a user to just come and say, yes, yes, I want to launch my own cluster, but I don't care what cluster size I'm going to launch. Here's my data, so I'm going to either upload it or maybe point the system at the data in S3. And what we generate is something called a personalized service level agreement, which is really a performance-oriented service level agreement. We tell the user, looking at your data and our system, we can offer you different service tiers. If you're willing to pay a certain amount per hour, in the backend, of course, this corresponds to a cluster size. So if you want this cluster size, which you don't care what it is, but here's the price for that cluster, for different kinds of queries on your data, we are going to guarantee different levels of performance. And then if you're willing to pay more, then some of the queries here are going to be accelerated and they're actually going to be much faster. And that's the kind of interface that we strive to provide. We have developed this in this PSLA manager system, which is also which is also available on our project website. So now the challenge is, of course, right? So given the data, we have a pipeline where we look at the user's data, we generate workloads, we predict the runtime, then we kind of compress all of that information to generate these SLAs. The second challenge is, of course, if I'm going to give you a runtime, it's very easy for me to give you an expected runtime, but can I guarantee it? So we actually are working on a system to actually guarantee these query runtimes. This is called Perf Enforce. At this point, we only had a demonstration on this, of this work. What we do is, once the user actually selects a service tier, they're going to write a query. As they write a query, we're going to directly say, specifically for this query that you just wrote, this is the SLA runtime that you have purchased for it. And then we're going to execute it. As we execute it, you know, the query might run faster or slower. In this case, maybe it ran much faster. We are using a cluster of 12 workers. So what the system is going to do is say, well, I actually don't need that many workers. Normally, the user, of course, wouldn't see this. This is for the purpose of the demo. We're going to shorten, kind of make the cluster smaller. And by doing this, we, the cloud provider, or saving money. In the other case where we run queries and we miss the deadlines, we're going to grow the cluster. And the question is, of course, what algorithms to use to grow and shrink the cluster. And here I don't have time to go into further details, but we have looked both at, control theory. So should this be a PI controller? And it shouldn't, because I'm not actually convergent to a cluster size. My mispredictions will go in different directions, so I will end up having to use different cluster sizes for different queries. Reinforcement learning can also have some challenges if it's kind of just learning from the past. What works really well is we start with a model of our predictions of performance, and these models are not quite accurate because they were built offline using other data sets. But as soon as the user starts to run queries on their data, we learn so much more about their data that we can improve our models. And using this online machine learning, we can converge much faster to really the cluster sizes for their machines and use that to get much better performance. And once again, I don't have time to go into more details, but I invite you to visit your website. So in conclusion, what makes Miriah interesting? So Miriah is this, big data management stack. We use it as a platform for research. It's available open source. It provides, the Miriah query language, which is highly expressive. It also has connections to Python and Jupyter notebooks, including user-defined functions in Python. We focus on providing high performance for different kinds of queries. I talked about iterative queries, but we also have other work in this space. We make it available as a service and also try to improve how we offer database systems as services. We also look at federated data processing, and the source code, including videos and the demo of the system are available online. And of course, special thanks to all the graduate students who are actually doing the work building the system. And of course, our sponsors for making it possible for us to build the system, and our science collaborators who are putting up with us trying to use the system as we're building it. So thank you very much, and I'm happy to take more questions.
All right, we're getting fairly close to lunch, so I'm gonna, if there's one question, we can take it now. Otherwise, there's an open lunch where you can
And I'm happy to take questions offline.
talk to Magda.
I have a question about the pipegen.
Yes.
So are you sure that the current implementation of pipegen can be run without any change with the new system? Like, so it kind of optimized with the source code of that DBMS system. Then if that uses like different pattern of generating the CSV file, then it might not work as you presented.
So we look at two different ways of generating. So we actually work with CSV files. We also work with JSON. So both work. And we consider two scenarios. We consider implementations that will manually build whatever strings they want to build to send over the network. And if there's a new system that does some kind of manual creation of the strings to send, then our approach will work, because what we do is that we actually look at exactly the source code that sends the data. We look at the strings that are being sent, and then we do data flow analysis to see where were these, at what point were these strings created. And we intercept the data by adding an extended data type, which is a string that acts just like a string, but it takes the data, doesn't create a string, just keeps it. That will work. If you use a system that actually uses some kind of library to generate JSON, so this is in particular for JSON, in many cases there's a small set of common libraries, so we have for some of them extended the libraries directly. That says, look, I know you're using this library, so I can extend it to do the same trick. So we work in both contexts. If you go beyond these, then that'll be interesting to see what actually is as another option and how that would work. Thank you.
Let's thank Magda again.